All right. Okay. So now we will, for the sake of this example, we will follow the same methodology that we had used before. Remember, we are designing a PI controller. So there are two design variables here. Okay. So we have two controller design variables. The typical analytic way we can deal with this is to basically make some choices for one of the variables, usually the integral time constant, and then study the other design variable, which is the gain, by using the root locus method. Okay, so we have kct and tau I, our design variable. An analytic approach is to consider some choices for tau I, some choices for tau I, and use root locus sketches with respect to KCT to make a final choice. Okay, so let us consider quite different choices for tau I to give us a rough idea about what's going to be the proper kind of range. So let's say that we can choose tau I to be 0.05 seconds. Let this be our first try, and then tau I is equal to 0.5 seconds, and tau I to be 5 seconds. So an order of magnitude different choices, and that's going to give us obviously very different root locuses for the remaining gain variable. Okay. Now, again, we want to see what's happening with respect to our reference input now. Okay, so by using superposition, we will we will kill the disturbance input, and we will derive the characteristic equation. Okay, so neglecting the disturbance, and with some algebra that I'm gonna leave to you, we can obtain the closed loop characteristic equation as Q of S will be equal to 1 plus KCT Z of S over P of S. So some zeros and some poles, and this is gonna be you can obtain this as KCT. The first term will be tau I S plus 1 over tau I S. Second term will be 0.9 over 0.1 S plus 1. These are for our inner loop gain set to 18. Okay, 0.8 over 2S plus 1. So now the first thing that you should note here is that there is actually a constant gain here. So in fact, when I am plotting the root locuses, I will be having a a total gain that's going to be 0.72 kct, and root locus with respect to k. Okay, so we will be plotting the root locus with respect to k, but there is a constant of proportionality between k and kct. When this becomes important, it becomes important at the critical points, like j omega axis crossing or the breakaway points and stuff like that. If you want to find those, you need to first find what's the k value, and then you need to convert to kct for your design. Okay, so we have one open loop 0, and we have 3 open loop poles. So open loop zeros are s is equal to minus 1 over tau I, one of them, and we have 3 open loop poles, and these are s is equal to 0, s is equal to minus 10, and s is equal to minus 0.5. Okay, so what is the number of branches? It is equal to the maximum of the number of poles and zeros, so we have 3 branches. What is the number of asymptotes? Number of asymptotes is equal to the difference, and it is equal to 2. So what is the angles of the asymptotes? Angles of asymptotes. We know that it is angle being plus minus 180 over m minus n, the number of the difference of the number of poles and zeros, and an odd number of them. So this is going to give us, as usual, plus minus 90 degree as the unique angles. Okay, so we have one asymptote going up and one asymptote going down. So this gives us an opportunity, because depending on where the asymptote crossing with the real axis, the centroid, is, the branches will be going towards the open loop zeros. One of them exists on the real line, the other 2 will be on the asymptotes. So the branches will be converging to the asymptotes, and if the centroid is properly located, we can actually have a nice closed loop pole locations as we increase the closed loop gain. Okay, so let's take a look at the first case, A, where our tau I is equal to 0.05 seconds. In this case, s is equal to minus 1 point tau I. It is equal to minus 20. Okay, so this is our 0 location. 0 at. So let me sketch this. So this is our first case. The real part, the imaginary part of the S-plane. Our poles are, one is at 0, the other one is at minus 0.5. It's difficult to draw this at scale. Hold on. 0.5 here. Then I have one at minus 10, and let me kind of break here at and minus 20. Okay, at minus 20 I have a 0, at minus 10 I have another pole. Okay, so now what is the real what is the part of the real axis which is part of the root locus? It's going to be this region over here, and this region over here. So there will be a breakaway point over here, but where would the branches will go? We will need to determine the centroid in this case. And the centroid is obviously a function of the value of the zero. Okay, so centroid
0.5 değil de 0.05 olması gerekmiyor mu?
hangisi? O pollarımızdan biri. Polumuz sabit. Zero'muz minus 1 over tau i'da. O da şu.
Şöyle yazmışız da tau i çarpı s yazmışız da transfer function tau i'de 0.05 seçince.
Şöyle oluyor. Yani zero'muz s is equal to minus 1 over tau i'da oluyor. Tau i'ımız 0.05 eksi 1 bölü 0.05 eksi 20 oluyor. Okey?
O 0.5 2'den geliyor.
Şuradaki 0.5 şuradan geliyor. Tamam. Pardon, gelmedi henüz ekranım. Yani o pollarımızdan biri. Onlar sabit. Pollarımız sabit. 0, eksi 10, eksi 0.5. Onlara bir şey yapamıyoruz. Ama 3 değişik farklı tau i'ımız var. Okay?
Anladım hocam. Teşekkür ederim.
Alright. Okay, so let me also calculate the centroid. So remember the centroid is the summation of the poles minus summation of the zeros over number of poles minus number of zeros. So that gives us simply minus 10 minus 0.5 plus 20 minus 20 makes plus 20 over 2. So what does that gives us? That gives us 4.75 if I'm not mistaken. Okay, plus. So you have a centroid somewhere along here. Unfortunately on the unstable side. Okay, so what's going to happen is that these branches will have to go towards the unstable region, okay, like this, and approach the asymptotes. So this is plus 4.75, the centroid. Okay, so you can see that this is not a very desirable case, because as k goes to infinity, in fact as you start increasing k, you are first of all squeezed into a very narrow portion very near the j omega axis, so you don't have let's say safe stability. And then if you keep increasing k, you will just go to the unstable side. Okay, is there any questions here? Let's take a look at the next example. So case B, where tau I is equal to 0.5 seconds. In this case, obviously we have 0 at s is equal to minus 1 over tau I, which is equal to minus 2. Okay, so we will have a slightly different case. Sorry, I cannot fit them side by side, so I'm gonna put it here. Okay, so here's our real and imaginary axes, our constant poles at minus 0.5, 0 and minus 10. Okay, now what I have here is a 0 at minus 2. Okay, new 0. Okay, so again we have the same thing with the real axis. So in fact not the same thing actually. We have this part being part of the root locus and this part being part of the root locus. And remember that locus starts at the open loop poles, and actually let me do this here as well, right? We have the direction like this, and we have the directions over here like this, and over here What's the new centroid is important. Centroid is equal to, again, summation of the poles, which is still minus 10.5, but now minus 2, which makes plus 2 over 2. So this now gives us a negative number, okay? Minus 4.25. Okay, so that's a much better location for the centroid, because our asymptotes are now somewhere over here, approximately minus 4.25. Sorry, it's not very to scale, actually. Minus 10 is much farther to the left, but you know, this illustrates what we are trying to say. So here the locus will go towards the left to the stable side and will approach the asymptote. Okay, let me draw it better like this. Okay. So this kind of looks like it's a much better configuration, because the asymptote is on the stable side. That means you can increase the gain as much as you want. There will be some consequences, like overshoots will increase and so on, because you are moving along the frequency of oscillations, right? If you keep increasing the gain, you will have larger and larger overshoot and faster oscillations. So we may not want to increase the gain indefinitely, but at least we are on the stable side, and we can play around with the gain to maybe, you know, achieve something, you know, desirable region. Okay? Obviously, it's symmetric with respect to the real axis. Any questions? Let's take a look at the last version to make our decision. Okay. So this looks promising, but we will see what happens with the last option, which is our C, where tau I is equal to 5 seconds. Okay. In this case, 0 at S is equal to minus 1 over tau I, which gives us now a 0 at minus 0.2. Okay, so new centroid at again minus 10.5 plus minus 0.2, so plus 0.2 divided by 2. So what's going to be that value? It's going to be minus 4.25. Sorry, 0 at 0.2. Yes, it is, I believe, at minus 4.25. Okay.
Bir öncekiydi galiba hocam.
Burada bir saniye, bunu bir hesaplayalım mı? Biri hesaplar mı benim için? Ne kadar?
Eksi 5.15.
5.15. Tamam. So it's on the stable side. That's okay. But now our 0 is quite at a different location. So we will see. We will need to see what happens. Okay. So let me draw this somewhat over here. Real and imaginary axes. Our pole over here, our pole at minus 0.5. Now I have a 0 at minus 0.2, and I have another pole at minus 10. Okay, and my asymptote is at minus 5.15, so somewhere around here. Okay, well, not very good. Let me correct that. Okay, somewhere around here. minus 5.15. Okay, so let's make our sketch. Now what is interesting is what's happening on the real line, because you see that for the entire gain range, I am now squeezed in this range between the pole and the zero. And over here, I have two poles, so I will start from the poles. I don't know where the breakaway point is. May not be exactly at the centroid, so let's sketch it like this. So it's gonna start from, or breakaway here. Sorry, it's gonna have a something like this. Okay. Now, so you see that, you know, closed loop dominant pole, or one of them, one of the closed loop dominant, sorry, the dominant pole is actually one. Okay, the closed loop dominant pole is squeezed within this range. Now, what's the implication of a closed loop dominant pole in this range? Two things. One is that it's very close to the j-omega axis. So if your plant model changes and the location of this closed loop pole changes, you may end up, you know, going to the other side, to the unstable side. That's the stability issue. But there is also the issue that the dominant pole is very close to the j-omega axis. Remember, a very small magnitude pole close to the j-omega axis means a very slow exponential in the overall response. Okay, so two results here: close to stability boundary and very slow dominant response. Okay, so we see that. Let's take a look at what we have. We have three options. One is that it just goes to the unstable side as I increase the gain, and you are basically constrained to this range. Very slow response, again, you know, very slow dominant response. Also close to stability boundary. Obviously, you can also cross the stability boundary if you increase the gain too much. So that's not very promising. B was very promising, actually, and C did not turn out to be that promising. So it did not help us to increase the integral time constant further. Okay, we around 0.5 we had a favorable response. Okay, so conclusion: overall, case B seems to be the best choice for tau I, with a suitable range of choices for K, and hence for KCT. Okay, remember KCT was related with K with a constant factor. All right. Any questions so far? Any questions so far?
Hocam aşağıya bir daha alabilir misiniz o şeyi?
Tabii ki. Now, is there any questions? Let me ask another question then to kind of work on. Now, what would be the closed loop behavior if we did not have the slave loop in the system, but the same PI controller. So we will neglect the disturbance, but we will look at what's going to be the response for a reference, okay? And what's going to be the kind of range of gain for the PI controller in this case for the same choice of tau I. Sorry, not for the same PI controller, but for the same integral time constant. So I still want to study what range for KCT for the same selection of tau I. Okay, so what I'm trying to see is if the inner loop did not exist, I had the original valve and the original plant, and let's say I had the same integral time constant, what would have been the range of KCT that I would be able to choose from? Okay, so that's one way of asking a question about the non-existence of the inner loop. Let me sketch what I mean by that. So T set. Okay, so I have again KCT 1 plus 1 over tau IS is my PI controller here. So this is my GC, let's say my only controller. And I have my valve 0.5 over S plus 1. So this is the original valve, and the original plant 0.8 over 2S plus 1. And we have the system output. Okay. Obviously, you may ask many different questions. For example, you might ask, what if the disturbance was there, but the inner loop did not exist? What happens then? What's going to be the transfer function for the disturbance, and so on and so forth? Okay. But for the time being, we are just studying what happens with respect to the set point. Okay. Let's write down the closed loop transfer function again. That's going to be simple in this case. 1 plus GC GV GP, and that's going to be 1 plus KCT, and the controller tau IS plus 1 over tau IS times the valve 0.5 over S plus 1, and 0.8 over 2s plus 1. Okay, so if you kind of okay, so you will just multiply this 1 by the denominator, so you will have tau I s times s plus 1 times 2s plus 1 plus kct times tau I and tau I. Okay, here I have tau I with the same selection that I did before. Okay, so here I will, okay, 0.5 second, okay, sec. So instead of tau I will just put 0.5 s plus 1 times 0.5 and 0.8. So we will have qs s cube plus 1.5 s squared plus 0.5 plus 0.2 kct s plus 0.4 kct. Now I will use, instead of root locus, I will use route Hurwitz, and when I use route Hurwitz, I don't need to really find a new gain with respect to kct with a constant factor, because I can write my route array in terms of kct directly, and I can find the range of kct that's available to me. Okay, it's equated to 0. Use route array, that means route Hurwitz criterion for stability range. Okay, so what is my route array? I'm gonna have s cube, s2, s1, s0. The first row is from the coefficient given to me, so I have 1, 1.5, 0.5 plus 0.2 kct, and then 0.4 kct. Okay, let's calculate the value here. A, it's going to be A is equal to 1.5 times 0.5 plus 0.2 kct minus 0.4 kct, sorry, I'm squeezed here, kct over 1.5. Okay, so you see that since 1 is positive, I need A being positive for stability. So let me write that down. So if I expand, I will have 0.75 plus 0.3 kct minus 0.4 kct will be the numerator. This has to be larger than 0 because the denominator is 1.5. It's a constant. Minus 0.1 kct is larger than minus 0.75. Therefore, kct needs to be smaller than 7.5. So there is an upper limit on kct. Now, in the previous example, remember, I was free to increase the gain to my liking, but when I removed the inner loop, I was limited from the top by 7.5 on my kct range. Also, remember, this is the number over here is A times 0.4 kct minus 0 over A, so this is 0.4 kct. 0.4 kct to be larger than 0, and therefore kct needs to also be positive. So I am limited from the bottom by 0 and 7.5 from the top. Okay. So note, now I have a much more limited range for feasible, let's say, controller gain. It might be interesting and fun to also use root locus to see why that's the case, what's the shape of the root locus. But it looks like in this new configuration, if you keep increasing kct, again you are crossing to the right half plane. Okay, so possibly there is again what's the order of the system? What's the number of I have still 1, 0 and 3 poles, so we have the same structure. We have a vertical twin asymptotes, so it looks like the centroid has been moved to the right half plane. Okay. In fact, let me do that. We have enough time. Okay. So the new root locus okay, our centroid is at -1 minus 0.5 plus 2 over 2. So we have it is at 1/2. Okay. Q of s is equal to s cubed plus 1.5 s squared plus 0.5 s plus kct times 0.2 s plus 0.4. So if I, in fact, okay, so that is 1 plus kct. I am putting it into kct parentheses here. So I will have 0.2s plus 0.4 divided by s squared plus 1.5s plus 0.5. So a quadratic term at the denominator over here. So this gives me s is equal to 0, one of the poles. And this one, if you factorize it, it's going to give us s is equal to -1 and s is equal to -1 over 2. So this is where the centroid is coming from. Okay? So let's make the sketch.
Bir şey sorabilir miyim?
Tabii ki, buyurun.
1 bölü 4 gelmiyor mu hocam burada centroid? Ben mi yanlış hesaplıyorum acaba?
Eksi 1,5 artı 2 eksi 1 bölü 4 geliyor, evet. Değil mi? Bir şeyi yanlış yapmadıysak eksi 1 bölü 2, evet. Değil mi? Eksi 1 bölü 4. Bir saniye. Eksi, özür dilerim. Artı 1 bölü 4 değil mi?
Evet hocam.
Tamam. Evet. Okay. Okay. So, are you guys clear about how I moved to obtain the open loop transfer function? Basically, in order to get rid of this extra constant, I remember the method of sketching the root locus with respect to any parameter in the closed loop characteristic equation. You group the terms with respect to a factor of that variable, kct, and then you divide everything by the factor of the variable of interest, so that you obtain a form that is 1 plus the parameter times a numerator divided by the denominator, and you treat that variable as if it was your gain. Okay, here it was really our gain, but this is the form that we get for our root locus. Okay, so let's also make the sketch, the real and imaginary parts. So I have a pole at 0, a pole at -1, and a pole, and a 0 at -2, and another pole at -1/2. Okay, and an asymptote at, let's make that kind of more to scale, somewhere over here at 1/4. Okay, so if I make that sketch, so it's going to be this region and this region. This region is by itself, right, starting from the open loop pole going to the open loop 0. Here I will have a breakaway point somewhere, and it's gonna cross to the unstable side. And now from the Raut-Horwitz, I know that this happens at KCT is equal to, what was the value? 7.5. Okay, at KCT 7.5, you cross to the unstable side. And also at K is equal to KCT equals to 0, again you cross to the unstable side. If KCT is negative, you will be in this region over here. Okay. Now, there is another interesting question here. Remember that I have taken tau I to be the same as the one I picked with the inner loop. So one question is that could I have picked a better tau I? Okay, that's a legitimate question. And let's think about that. Okay, it's all about the location of the centroid. Okay, so well, we need to somehow push the centroid to the negative half. That means the stable plane. Okay. So what is the centroid? Centroid is the summation of the poles minus the summation of the zeros, and the 0 is related with the integral time constant. So I will have minus 1.5 from the poles plus 1 over tau I divided by 2. Okay? So in order for the centroid to be remaining in the negative plane, you need to make tau I larger in this case. Okay, so make tau I larger, so that you have a smaller integral coefficient. Okay, for example, let's tau I be equal to 4 seconds. Okay, so we have a 0 at s is equal to minus 0.25. In this case, our centroid is minus 1.5 plus 0.25 over 2, and centroid is now at 0.625. You see that you're really kind of, you don't have much to do, because tau I is necessarily positive. So as you increase tau I, yes, this positive term diminishes, and so you have just a little bit pushing to the left, but it is bound by minus 1.5 divided by 2. So you cannot go any further to the left than minus 0.75 in any case. Okay. So in this case, let's make the sketch and finish for today. Okay. So the new root locus is basically so you have over here your pole at 0, minus 1/2 and minus 1, and you will have a 0 at minus 0.25. Okay, so the sketch will look like something over here, something over here, and our asymptote will be somewhere in between, so that these will meet, okay, and then branch away to the asymptote. Okay, we don't know how exactly, but it's gonna look roughly like this. Okay, again, you know, system very slow. Okay, due to dominant pole. Also close to the stability boundary again, right? So that kind of concludes the example, and this is actually where you will be responsible too. Okay, so exam scope ends here, but tomorrow I will also talk about as much as I can from the disturbance feed forward control tomorrow morning, but this basically concludes what you will be responsible of. Any questions so far? Arkadaşlar, soru var mı? Anlaşılmayan bir şey var mı buraya kadar? Peki arkadaşlar, o zaman yarın sabah görüşmek üzere son ders saatimiz için. Kendinize dikkat edin.
İyi günler hocam.
Görüşmek üzere.